Let's take all that we know until now and combine it, and this is going to be the basis for a few setups. So let's just first set the platonic solid to be an icosahedron again. Let's delete all this down here, so we're stuck with this VDB from polygons here. Let's drop down a null first, because what we want to do later is put that setup that we're just building into a solver. So this will be our input from the solver then. Let's call this in. And the first thing I want to do is drop down two VDB analysis subs. Let's just copy this one and call one grad for gradient and the other one curve for curvature. Wire in the input to both, and let's set up this to be a gradient. And when we middle mouse button on this, we see the volume is called surface, so it should store our gradient. So let's just rename this. We can select a custom name here and just call it gradient. Let's set this VDB analysis up to yield our curvature, and also let's call this curve. Now, what I want to do, I would like to use the curvature of my object to drive the strength of the advection, because in essence what I want to build is the same setup as we did in the two previous projects, but now I want to drive the advection by the curvature. So in essence what I need to do is I need to multiply the gradient and the curvature, but also I have to take care of these weird values that curvature yields sometimes. So I should remap this, and let's do all this within a volume VOP. Let's drop that down in here. Pipe in the gradient in the first slot, the curvature in the second, and then dive in there. And the volume VOP works really similar to the point VOP or the attrib VOP. So in the end, what we want to output with a bind export is a float called gradient. So this is going to be our output, and we would like to sample those two fields coming in here with a vol sample and a vol sample vector. So the sample vector is for the gradient coming in through input 1, and the sample scalar is for the curvature coming into input 2, and both need the current voxel position, which is p. No, p I told you, like this. Same here, like this. Now let's take care of remapping that curvature value. And the first thing I'm going to drop down is a fit node, fit range node, where I pipe in that curvature value here, and specify a minimum and maximum value. And let's just arbitrarily go from -10 to 10. This is a value that in previous setups kind of worked for most geometry types. So after we've done that, let's drop down a ramp, set this to be a spline ramp so we can remap the curvature as we like, and finally multiply both the curvature and the gradient with a multiply node. Pipe in the gradient first, and then the ramped and fitted curvature, and output this as our new gradient here. We read in the gradient on the one input and the curvature on the other input, then fitted the curvature from -10 to 10 into the range of 0 to 1, and then use a ramp node to be able to influence that range from 0 to 1, and then just multiply the gradient with that value we generated. So we basically scale the length of the vectors in the gradient. Okay, after we've done that, let's drop down a VDB advect again, pipe in our incoming geometry in here, and our vector field that we just created in here. Let's just middle mouse button on this to see, yes, we have a gradient field coming through here. Perfect. One thing we might later do is add a smooth in here to smooth out the gradient, or maybe up here before we divide the VDB into the two VDB analysis nodes, maybe add a reshape node to dilate the VDB, but we can see that later. For now, let's just highlight this, and we immediately see that our volume only gets advected around the areas where there is curvature, which is exactly what we like. Also, within here, what we can do is remap the curvature value. So for example, when I dial this end up to a value of, say, 10, I can now see my VDB advect is really aggressive, and it already truncates some of those values. So let's dial it down to 1, copy this bunch of nodes, and put it into a solver. Wire in our VDB, paste our node chain here, wire this up, highlight the VDB advect, and then highlight the solver and hit play. Well, we see at a certain point this yields artifacts which can look interesting, but during the first stages we see exactly what we suspect happening. The area around the edge gets advected more and more, And again, after this geometry is created, it's again fed into the solver. So now we have more curvature on this area here, which is producing these intricate and interesting structures. Let's try and drop down a smooth after we created the gradient here. Style in a voxel radius of 2 and maybe 6 iterations, and let that run. Maybe that was a bit too much smoothing, although let's see where this goes. Just let it run. Let's stop that. That is so-so. So let's try tweaking in here. Disable this for a while. What we could also do is smooth the resulting VDB that comes out of the VDB advect with a VDB smooth SDF. Wire that up here. Let's see how that evolves. Well, does more or less the same, so let's stop that as well and try finding some nice parameters for this. Looks a bit like a corn cob. Not too interesting either. That's not on point either. That looks a bit like a mutated soccer ball. Now it gets a bit more interesting. Well, nevertheless, the main parameter that you'd like to tweak in this setup are in the solver, in the volume ball, actually, this curve and also the fit node. So the source minimum and maximum, as well as this ramp parameter that you're going to tweak and work your way through. And this might not look like much, but this is going to be the basis for a few very interesting future setups. So let's just clean this up. And it's a very compact setup. So let's just save this for now and build something a bit more advanced on top of this.